Welcome to our inline introduction to the science of QSAR. This course is provided to give students of the QSAR application toolbox a general overview of the science of QSAR and how it is being implemented in the QSAR application toolbox being developed by OECD and Paris. The course is broken down into 4 parts. The first one being a general overview of the science of QSAR itself. A second part to show how trend analysis is used in the formulation of QSAR and the interpretation of estimation techniques. Third part is a more formal look at the formation of chemical categories for filling data gaps when you have chemicals that have not yet been tested. And then finally, a general overview of the QSAR application toolbox itself and how these concepts are being incorporated into the toolbox. There are 3 simple ideas that QSAR is concerned with and that we should emphasize right at the outset. There is a concept of an endpoint or some measure of chemical activity. It could be chemical activity in a biological system and commonly called biological activity, but QSAR is concerned with selecting measures of biological activity or chemical activity which it calls endpoints. We'll discuss a fair amount about the number of endpoints needed to really characterize the hazards of an individual chemical and how this complicates the science of QSAR. The second concept is the idea of structure and how you can quantify this. In other words, how you can take the shape of a molecule or just the picture, a graph of the molecule in 2D, and transform that into a numerical value that has some basis or bearing on the way the chemical is likely to react. And then the third general concept is one of mechanisms of how a chemical structure can interact with biological systems to cause the effects that are observed and used as endpoints. These 3 concepts of defining endpoints, of trying to quantify structure, and try to classify a chemical by the different mechanisms of interaction constitute most of the work that is going on in the science of QSAR. For the outline of this course, we are going to just review briefly the need for predictive methods. Why do we need QSAR? Why would we bother? Then go into the basic terminology that's used in the development of QSAR models, review of some of the factors that are important of selecting biological endpoints for modeling, a look at using trends to define chemical categories. Much of your time in the use of the toolbox, or to become proficient at the toolbox, will be involved with how do you define chemical categories using trends analysis. Then, how do you take the chemical categories that are formed in the toolbox and use these to fill data gaps for chemicals that have not yet been tested? Finally, we'll give you a brief overview of the QSAR toolbox itself. Many of you have a background in hazard assessment or providing data for some form of hazard assessment or hazard identification. Therefore, it's not surprising that when we try to characterize the hazards of a chemical, we have to use a wide variety of biological responses, and those require laboratory measurements of the chemical toxicity. Laboratory measurements usually provided through a standardized test guideline. But in the hazard identification of untested chemicals, the number of laboratory measurements is very large and involves many exposure scenarios, time and species and so on, to really adequately capture the hazard of the chemical. Regulatory risk assessment for the last 50-60 years has relied heavily on the interpretation of those bioassays. These risk assessments are designed to reveal the spectrum of effects that might be caused by a particular chemical. And in fact, many of those laboratory measurements or test guidelines are grouped together into batteries of bioassays intended to characterize important hazards, such as short-term effects, acute toxicity, carcinogenicity, mutagenicity, reproductive impairment, developmental deficits. A very wide array of potential hazards that should be evaluated to some level for chemicals that are finding their way into the environment or being exposed or having humans exposed to them. Since not all chemicals can be tested for everything, there are multiple levels of hazard assessment or risk assessment, and screening level assessments, a lower tier used primarily for priority setting or maybe some classification, can cost as much as $1 to $5 million just to provide an array of biological effects that are caused by a chemical. And when you get into the more comprehensive risk assessments, it's not uncommon to have them exceed $60 million for a single chemical. Due to the high cost of these animal tests, risk assessments based on actual data are limited to a very small percentage of industrial chemicals. Fewer than 10,000 chemicals have ever been tested for the major hazards, and the majority of the chemicals that have some data available for them have data on only a few of the potential hazards of the chemical. The world inventory of chemicals in commerce right now exceeds 160,000 chemicals, and it's likely growing at a rate of more than 3,000 new chemicals each year. So there are a large number of chemicals in production, and fewer than 10% have any data associated with them at all. This creates a situation where we know a lot about a little, and the more time spent on any individual chemical means that there are many other chemicals that for which we know nothing about, and we just have to hope that they're not causing significant harm in the environment. But more importantly, the time required to do the interpretation of the data and produce even an initial hazard assessment, such as the SIDS initial hazard assessment. The time required to do this is so long that the collective capacity of all the OECD member countries can only do 500 chemicals a year or thereabouts, even though we know that new chemicals are coming onto the market much faster than that. So using the conventional approach of testing all hazards and taking the time to interpret the data simply will not allow us to evaluate many of the chemicals. Alternative tests methods that are more diagnostic of particular hazards and much faster are one leading approach to filling the data gaps. That is, if we have inadequate data for chemicals, then we should find better ways to do it faster, but we'll use the same old approach of trying to interpret toxicity data for all chemicals in doing our risk assessment. Non-testing alternatives, of which QSAR is the primary example, but non-testing alternatives involve the use of chemical models and the data that's available in the literature. So we use chemical models to extrapolate the hazards of tested chemicals to similar untested chemicals. Those relationships, or those methods of the non-testing alternative methods, is centered largely on the use of quantitative structure-activity relationships, from which the QSAR acronym is derived, that simply relate biological activity to some structural feature in the molecule. While this is new to toxicology, physical chemists, engineers, and medicinal chemists have been reliably estimating the behavior of untested chemicals for more than 60 years. So this is not a new field, but it is being applied in a new area and in a very complex area. I should say that medicinal chemists have focused on drug design, whereas hazard assessors are really looking not at the efficacy of a chemical to do a certain job, but all other possible side effects of the chemical. So it is much more complex to apply QSAR to hazard assessment. So let's look at some basic definitions in QSAR. First of all, chemistry is based on the simple premise that similar chemicals will behave similarly. If two chemicals appear to be very similar to you but have dramatically different behaviors, then your perception of similarity is wrong, because if they are truly similar, they will behave similarly. If you have biological data that shows a dramatic difference between two chemicals, that data is telling you they are not similar. And many times the subtle differences in chemical structure that cause those big differences are not easily visualized, and they certainly cannot be seen by looking at a graph of a chemical structure or the number of atoms or something simple like that. Like most complex systems, the behavior of a chemical as a molecular system is largely derived from the electronic and steric properties of molecules, and it is only through the quantification of electronic and steric properties that you can really judge similarity. Therefore, the field of QSAR is concerned with methods of quantifying similarity in order to improve our ways of grouping similar chemicals. More importantly, similarity is not an absolute, but it must be determined within a specific context for a specific attribute or behavior. That is, to judge similarity just as you would within a group of people, you have to have a certain question in mind in order to decide whether these two people are similar. And more importantly, you need to recognize that chemicals can be similar and different from each other, similar to and different from each other simultaneously in many different ways. For toxicology, a structure-activity relationship would begin with a test endpoint, and I would like to just say, for a simple example, the test endpoints might be a lethality endpoint like LC50, or an effect concentration like a EC50. These are the measures of activity that one can be reproducibly measured in a laboratory test and are relevant to the hazard assessment that's being conducted. QSAR searches for a relationship between the chemical structure and activity so that the test endpoint can be predicted accurately from structure. In a simple example, let's take the definition of an inhalation hazard in many countries would be just an industrial chemical that has a LC50 for a 4-hour rodent test, which is less than 20 milligrams per liter in the vapor. If it is more toxic than that, it would be considered to be an inhalation hazard. So to screen many untested chemicals to decide which ones are going to pose the greatest hazards by inhalation hazard, we could compile a list of LC50 values for 20 or 30 chemicals of the ones that have been tested, and then represent chemical structure using vapor pressure, and we'll explain why we would pick that in this particular case right now. But we use vapor pressure as sort of a structural method of quantifying structural variations, and then see if there is a relationship between the vapor pressure and the LC50. When you do this for narcotic chemicals, you get an equation, a regression equation, that is simply the log of the LC50 for the rat 4-hour test. The toxicity of the compound is equal to 0.69 times the log of the vapor pressure plus a constant. This equation then allows the LC50 of untested similar chemicals to be estimated. The caveat I would like to add right here is I've underlined the word similar, because this, when you build a model for a specific endpoint like LC50, you cannot expect it to then predict a different endpoint, different time, different species, or whatever. It is only for that specific endpoint, and it is only for that specific group of chemicals, or any of those that are similar to that training set. I'd like to turn now just to cover a few important things about biological endpoints, because you will find there are many biological endpoints in the QSAR application toolbox. The purpose of QSAR would be to develop models that allow us to estimate important toxicity estimates for thousands of chemical structures in order to focus our attention on those chemicals that cause the greatest risk. But since an individual QSAR model for a toxicity endpoint like LC50 is only reliable for chemicals that are similar to the training set of those chemicals, this creates the need for a large number of QSAR models. In other words, we have to have a different model for each endpoint and each class of chemicals that would be considered to be not similar. In other words, have different toxicity mechanisms. Similar chemicals are usually defined as those that cause effects through the same toxicity mechanisms. I mentioned narcosis, but there are many mechanisms by which an animal can be killed quickly. Uncoupling oxidative phosphorylation is one method. Neurotoxic agents such as cholinesterase inhibitors are sort of classic examples of mechanisms which are capable of producing lethality in a very short period of time. For each mechanism and each LC50, in other words, for rodents, mice, rats, dogs, fish, birds, each of those would need their own QSAR models. And just as an aside, there are about 25,000 QSAR models reported in the literature for specific endpoints and specific groups of chemicals. The matrix is just very large. Thus, the QSAR models first have to predict or select whether a chemical has the same toxicity mechanism as the training set in the chemicals that were used in building the particular model. If the chemical's toxicity mechanisms differs from the one for which the chemical was built, it is by definition not similar, and its effects cannot be reliably estimated from the same model. So the steps that go into developing a QSAR model are fairly simple. First of all, we have to choose a well-defined endpoint of biological activity that we want to use, and then with that endpoint in mind, compile measured values for the chemicals that have been tested. And usually, although it's not always possible, but we try to would gather data that were where the measurements were made with a consistent test method or for similar chemicals. Many times the scientists doing the testing are not trained in QSAR, and the chemicals selected or provided with their test data have never been tested for similarity or evaluated at all. So a way around that would be to select a homologous series of relevant chemicals, like a whole series of chlorinated benzenes or something like that, a homologous series of relevant chemicals, and then systematically test those for the biological activity endpoint being used. You will see when you look in the QSAR toolbox that there is a very large systematic database for acute toxicity to fish in industrial chemicals, and this is because we used the industrial inventory itself and clustered them, took representative chemicals from many different classes and tested them all, tested about 700 of those consistently so that we could produce QSAR models for that fish toxicity endpoint. Unfortunately, that has not been reproduced or repeated in the mammalian toxicity literature, but we'll get into that later. So once you have a series of chemicals with a well-defined endpoint, the next step is to identify the chemical attributes that are likely to be important in the toxicity mechanism and the endpoint under consideration, and then calculate for those something called a molecular descriptor, which is just a term that is used to say how can I represent chemical structure and important attributes of structure in numerical terms. Many times quantitative structure activity relationships is considered to be a term where you say I am interested in quantitative relationships. The emphasis being on for quantitative is it's modifying basically the term relationship, but in fact most of the time the term quantitative is modifying structure. You are quantifying structure and relating that to activity. So if we have an endpoint and we've gathered data together in a file and then calculated molecular descriptors, and there may be 2 or 3 that you think are important. In some schools 1,000 different chemical descriptors would be compiled for each chemical structure, and then using normal exploratory statistical methods we explore the variances among the various descriptors and endpoint values and identify quantitative relationships or some kind of relationship or clustering between quantified structure and the various endpoints in the assessment. So those are the simple steps to producing a model from a set of training data or experimental data that is useful for a hazard assessment. Let's just go through a simple example of this to make sure we have this all in mind. And it's a little bit awkward with the slideshow like this, but we may have to jump ahead to the next slide and then come back to this. But basically we are compiling, let's say we're going to compile data for lethality, the LC50 again, this time in mice, a different species. and the lethality that can be produced in a 30-minute inhalation exposure. This example was chosen primarily to show you that if we do the same thing that we did in the fish toxicity modeling many years ago were done in the mammalian system, we would get the same kind of results. And it turns out that a 30-minute inhalation test for lethality is one of the screens used in the anesthesiology literature. In the example that I've picked in the next table, and if you want to jump ahead you can see what the table looks like, but in this example, restricting the chemicals to simple aliphatic ethers is somewhat like the homologous series that increases the likelihood that the toxicity mechanism for lethality with all of those chemicals are likely to be the same. In the next slide we have the tabulated data for a whole series of aliphatic ethers, and we then calculate or measure the vapor pressure, find measured values for the vapor pressure as a molecular descriptor used to just quantify the structure of the chemicals for what we think would be the toxicity mechanism of narcosis. If we just use a simple correlation analysis, regression analysis on the LC50 values with the vapor pressure, you get an equation much like the one that we showed with the example of the rat, but in this case the log of the LC50 is a 0.57 times the log vapor pressure plus 2.08, a constant again. In other words, a simple linear regression analysis that as you decrease the vapor pressure, you also decrease the LC50 or increase the toxicity. It's kind of counterintuitive, but that is the way lethality and vapor pressure vary. This regression equation is the new QSAR for this endpoint and this class of chemicals. Even though the toxicity mechanism is known, it's just presumed that these are all probably going to produce lethality by the same mechanism. On the slide with the list of chemicals, this is just for showing a real live example, and I'm not going to discuss this in any detail. We'll move to the next slide. There are a couple of things to notice about the example that I've shown in this case. First of all, the dependence on vapor pressure, in other words the slope of the linear regression, is almost the same as the QSAR derived for the 4-hour exposure in rats, which really suggests that the same structural features are involved in both sets of chemicals and both endpoints, and they're controlling toxicity. And in fact, we've recently published a paper where we've expanded this basic line to many, many, many other volatile chemicals and solvents and so on to show that this is a measure of baseline toxicity or narcotic, non-specific, reversible up to the point of lethality toxicity by inhalation. Notice that the intercept for the mouse model is about 0.5 log units greater for the 30-minute test with mice versus the 4-hour test with rats. If we assume that the toxicity mechanism causing lethality is the same for the chemicals in both sets, can you give an explanation of why the LC50 in the mouse is greater that is lower toxicity than the LC50 in the rats. Again, this is not to be a trick question in any way, but to show that the interpretation of the data, when it is consolidated in the form of a model, can be physically interpreted. In other words, if you try to produce lethality in a shorter period of time, you generally have to have a higher concentration to reach the lethal threshold in the same amount of time. So it might appear to be less toxic in a short-term test, and the toxicity drops to the incipient lethal threshold, usually sometime after 4 hours in an animal. Another variable in here is just the size of the animal itself. A mouse is smaller than the rats that were used, and in this case probably actually lowered the comparative biological activity endpoint for the mice. But the differences of the intercept between regression equations usually tells you something about transport and other factors that are influencing the stability of the biological endpoint that you're using. If you do a test, if you run a test long enough and get it to a steady state condition, then you find that the time dependency on the biological activity is not as important. But in this case, the statistical exploration of the data for many different chemicals is one of several important methods for defining chemical similarity itself. The fact that these data can almost be superimposed on each other, they have the same slope, and all suggest that they are behaving similarly. This QSAR implies that vapor pressure is a really important factor in determining the potency in this lethality test. If you picked many other molecular descriptors, you would find that many of them would not correlate with toxicity at all, and it shows that they're just not relevant to the processes and the activity of the chemical in this particular test environment. The good correlation here points to structural attributes that influence boiling point or vapor pressure, and since vapor pressure and boiling point co-vary to some degree, the same kind of intramolecular and intramolecular forces, such as degree of branching, presence of polar groups, shape of the molecule, all of hydrogen bonding groups, all of these things affect the vapor pressure. And but the point is, the vapor pressure is a measure of thermodynamic activity and chemical activity in a general sense, and this seems to be a good predictor of a non-specific lethality mechanism like narcosis. Chemicals that cause lethality by other toxicity mechanisms, an example here would be acrolein or phosgene, would appear as statistical outliers. They would appear, the LC50 of these compounds are much lower than the aliphatic ethers at the same vapor pressure. In other words, they're statistical outliers. They show up very quickly, and when you see an outlier in a set of data, you know that you have more than one mechanism or a new mechanism operating, and that is why the chemical toxicity appears to be different. Therefore, in QSAR, outlier analysis is often used to gain insights into chemical similarity, and in fact, as you'll see in the toolbox, is used to define the terms for a common mechanism, even though you might not know what the specific details of the mechanism is. A common criticism of QSAR is that we have some chemicals that look similar and behave differently, and just this little bit of change causes a dramatic change in toxicity. And once again, where this is commonly used to show that QSAR doesn't work, and in fact what it's saying is your whole perception of what is structurally similar is just simply wrong and needs to be upgraded, and then you would not expect the two chemicals to have a similar biological activity.